You know how sometimes physics feels like it's written in a secret code? A language just full of strange symbols and rules? Well, today, we're going to crack that code. We're opening up the physicist's toolbox to show you the essential math that makes the entire universe tick. And I promise, it's way more intuitive than you might think.
Okay, so let's just dive right in with a really simple idea. At its absolute heart, physics is our attempt to describe the world around us. You know, from a planet orbiting the sun all the way down to the friction that lets you walk across the floor. It's the what and the why of, well, everything. And this is the key. Math isn't the scary part, it's the helpful part. Think of it like a collection of tools. You know, your rulers, your wrenches, your blueprints. These are the things that let us take those descriptions of nature and actually build a clear picture, a real understanding. Today, we're grabbing a few of the most important tools right out of that box.
So what's actually in there? We're about to pull out the essential tools that physicists use every single day to make sense of motion, forces, and energy. You ready? Let's get started.
First things first, we need to know what we're actually measuring. See, some things are super simple, like temperature. 30 degrees Celsius, that's just a number. We call that a scalar. But what if I told you to walk 5 meters? You'd immediately ask, which way? And that's a vector. It has both the size, the 5 meters, and a direction, east. And believe me, physics cares a lot about direction.
So let's really get into our first tool, these things called vectors. It's so much more than just an arrow on a page. It's a fundamental concept for describing pretty much any movement or force out there. Let's see how it actually works.
A vector is just an arrow. That's it. The length of the arrow tells you how much of something you have. We call that its magnitude. And of course, the way the arrow points tells you the direction. So a 20-kilometer-per-hour wind blowing north is a totally different vector from one blowing east. Even though their speeds, their magnitudes, are exactly the same.
Now the really cool part is how we combine them. Let's say you walk 3 meters east, and then right from that spot you walk 4 meters north. Where do you actually end up? Well, you don't just add 3 and 4 to get 7. Nope. Instead, you draw a new arrow from where you started to where you finished. We call this the tip-to-tail method, and that new arrow shows you your final displacement.
And this isn't just some abstract idea. It's happening literally all around you. If you try to swim straight across a river, what happens? The current pushes you sideways. Your final path is the sum of your swimming vector and the river's current vector. It's the exact same reason a pilot has to account for wind, and it's precisely what your GPS is calculating with every single turn it gives you.
You know, sometimes it's actually more useful to do the opposite of adding. We can take one complicated diagonal vector and break it down into 2 simpler ones that are perpendicular. So like one part that goes forward and one part that goes up. This is called resolution, and it's incredibly useful. I mean, think about pulling a suitcase at an angle. It's only the part of your force pointing forward that actually helps move it along. And finally, with vectors, we can combine them in 2 really special ways. First, there's the dot product. This basically measures how much 2 vectors are aligned. So if you're pushing a box, the dot product tells you how much of your push is actually helping the box move forward. But then, there's the cross product, and that's all about rotation. Think about using a wrench to tighten a bolt. You apply a force, that's a vector. At a distance from the center, another vector, and the result is a turning effect. That's the cross product right there in action. All right, let's put the vectors down for a second and pick up our second major tool, graphs. But hey, don't think of boring charts and data points from school. To a physicist, a graph is a story. It's a visual narrative, a picture of how one thing changes in relation to another. And we can read these stories by looking for 3 key clues. The slope, which is just the steepness of the line, tells us how fast something is changing. The area underneath the line tells us the total amount that's been accumulated. And any curve in the line tells us if that rate of change is actually speeding up or slowing down. Let's start with slope. Just imagine a graph of the distance you've walked over time. A really steep line means you covered a lot of distance in a short time, so you were moving fast. A totally flat horizontal line means your distance isn't changing at all, you're just standing still. The slope of a distance time graph is your speed. It's that simple. Okay, what about the area under the graph? Oh, this one is brilliant. If you have a graph of your speed over time, the total area under that line represents the total distance you traveled. It's like you're adding up the little bit of distance you covered in every single tiny moment of your journey. It's amazing. So, now we have our tools, right? We've got vectors for direction and graphs for telling stories of change. Now we can finally put them to work. And this is where it gets really cool, because these tools help us spot the fundamental patterns and the simple rules that the entire universe seems to follow.
And what's wild is that so much of physics boils down to just a few of these patterns. Let's look at the big three. First, you've got a linear relationship. You double the input, you double the output. Simple. Like how your weight is directly proportional to your mass. Then there's the quadratic relationship. With this one, if you double the input, the output gets 4 times bigger. This is a huge deal for things like a car's braking distance. And finally, we have the inverse relationship. You double the input, and you cut the output in half. Just think about how pressure works when you press down with your finger.
Okay, we've covered a lot of ground here. We've seen how vectors give us size and direction, how graphs tell us stories about change, and how just a few simple patterns seem to govern everything. So it's time for a quick toolbox checkup. Let's see what you picked up.
First question. So on a graph of speed versus time, remember that the slope tells us the acceleration. So if that line is perfectly flat and horizontal, what's the acceleration?
The answer is 0, right? A flat line has 0 slope, which means the speed isn't changing at all. And if your speed isn't changing, your acceleration is 0. You're just moving at a constant velocity. See? You're already reading the stories in the graphs.
All right, next one for you. Think back to our vector products. To open a door, you need to create a turning effect around the hinges. So which product describes that turning motion? Is it the dot product or the cross product?
It's got to be the cross product. Remember, the cross product is all about rotation and turning effects, what we call torque. Pushing straight into the door won't make it turn, but pushing on the handle away from the hinges creates that perfect turning force.
Last one. Let's think about those patterns. We mentioned that a car's kinetic energy has a quadratic relationship with its speed. So if you double the car's speed, how much does its kinetic energy increase?
It increases by 4 times. That's the power of a quadratic relationship. Doubling the input, your speed, results in a quadrupling of the output, your energy. And that's absolutely critical when you think about things like physics and especially road safety.
So there you have it. The toolbox is open. You've got vectors to handle direction, graphs to read stories, and patterns to spot the fundamental rules of the game. The real question is, now that you know what to look for, what kinds of patterns and stories are you going to start seeing in the world all around you?